All right. Good morning, everyone. I want to welcome all you folks to the second day of the first ever Georgia First Virtual Symposium. This is session one of the day, and it is a Java command-based template programming hosted by Brian Carlson. So, Brian, take it away.
Good morning, everybody. Let me just get something up here. So I saw the survey results, and it looks like in this class we have people that basically have got a bunch of students, 80% of your students, and 60% of you have just a little bit of experience with the command-based template, and 40% of you are using it, which is great. So hopefully you can get some information out of this session for you. And then 60% not sure, and that's fine, because a lot of people who are new to programming on their team may not know what they're using. So let's get started about the command-based template. One of the things that I like to point out about programming, and I'm glad you guys are here, is Steve Jobs' quote: "Everyone should know how to program a computer because it teaches you how to think." And so programming is really about organizing thoughts and having well-structured code. And as you get more and more into a software path, and if you go into software development as a profession, logically sort of breaking things apart is a really important thing. Let's go over here. So the reason why I want to look at the command-based template is you don't want spaghetti code. Spaghetti code is code that is very disorganized, and you can't see a sort of a principle behind how the code is. If you understand how the code is sort of designed, you're trying. Yes? Hello?
You're there. Keep going.
I thought you said something. So by understanding the philosophy behind the code, you kind of know where to add stuff. And if you find a bug, or if you have a bug, you know where to go to fix it. So the command-based template has several different benefits that sort of address those issues. It's a very clean way to organize your code. And you'll see there's a couple of major building blocks of a command template. Because it's so structured and organized and things are segregated, it's easy for you to add building blocks from year to year. So you could open source your code this year, and you could reuse it, and you might be able to use a lot of it and just add some more functionality depending on how you write your code and some of the game needs. The other thing with the command-based template is it is the recommended way by first to program. So if you use it and I use it and all the other teams use it, when you go to competition and you're like, I have a problem, could you help me? Everybody knows where it's at because they know the structure. They know where it should be, and if something's different, they can spot it. So that's the benefits of why you should be using the command-based template. So basically, the command-based template falls, I talked about building blocks. And there are two building blocks that are in the command-based template. There are commands and subsystems, right? So if you look at what are commands, things might be move to scoring position. They might be drive forward. They might be, drive to goal. Then on the opposite side of the spectrum, you have subsystems. And subsystems, you might have a drivetrain, a wrist, or an elevator, right? So these two clouds are very dependent on each other, but they're separate in their clear logical distinctions, because fundamentally what happens is commands are your actions. Think of it as the function you want the robot to do, where subsystems are really your hardware. So anything that's talking to hardware really better be in a subsystem, not in a command. So that allows you to abstract the hardware from what you want it to do, and you can see how if you have a drivetrain, I'm guessing next in 2020, 2021, you're going to have a drivetrain. I'm pretty sure in 2022, you're going to have a drivetrain. Unless there's a water game, you're going to have a drivetrain. So you can reuse that subsystem every year, all right? And you're probably going to need to drive it. That could be reusable. If you have a shooter, if you have some commands for shooters, you could eventually later on have different types of shooters where you can then start growing this command base. We all know that programming has very little time to program once they get the bot. If you start building up this library of functions, it allows you to be that much further along when you get the robot. So we know we've got these commands and we've got these and these subsystems. Well, how they all sort of kind of work together. And so what happens is, if you think about the pipeline, you have buttons, and the button will trigger a command, right? Because that's what the user is going to touch. The command will then control the subsystems, right? So it knows what it needs to use, and it goes about and calling those things. And the subsystem is going to control your hardware. So that's kind of your stack of operations, right? Buttons, command, subsystem. Further down you go, the more you get to your hardware. All right. Now, before we get into a lot of the detail of how these are all sort of wired up, because there's some really cool stuff there. In 2020, they've changed the structure of the command template and WPI-lib. And one of the things they did was make the structure of the template and WPI-lib in a way that it is more reflective of industry standards that software engineers do, right? So it's still just as simple to program. I usually say in 50 to 100 lines of code, you can get your robot working. You can do more and do more fancy stuff, but the basic doesn't take that much. And so even though they did the change, it does not take, it still takes the same amount of lines of code. You're just now doing things in a way that if you go into software engineering, these will be concepts that you'll be using. So one of the things I want to talk about is inversion of control. So here's the formal definition. Conventional dependency relationships established between high level, whatever. All right. So what you'll find in software engineering is there's lots of buzzwords, right? And so you're stuck with trying to learn buzzwords while you're trying to learn concepts. So what I want to do is ignore all that garbage and talk about something you know, a Keurig. So if I have a Keurig, I can make coffee. What kind of coffee can I make? I can make whatever coffee I have a pod for. So if I want to make, let's say Dunkin' Donuts has some good coffee. I don't drink coffee. But if I want to make Dunkin' Donuts coffee, I can get a Dunkin' Donuts pod. There's one problem. If Keurig doesn't want to license and have Dunkin' Donuts pay them for making the pods, there's not going to be a pod available. So at this point, my coffee maker is telling me what I can drink. I want to drink what I want. It's my choice, not my coffee maker. And so I don't want this pod thing, right? As a matter of fact, in the real world, with the Keurig, they actually came out with a new version where it actually, so the first version, people realized they can buy this little cup and put what they want into it. And so they can make the coffee they wanted. Well, the next version of the Keurig came out and there's a little RFID tag or something inside that little tear-off lid. And if you didn't have that tag, you couldn't use your coffee. So all those little mesh things they could put in there didn't work. So then they're like, well, again, I don't want my coffee maker telling me what to do. So people then started taking the little tear-off paper off the top of those things and put it on top of their little mesh container, getting around it. Because it's really, it's not real friendly to the user if you are telling the user what they can do. All right. So that's inversion of control. All right. So, sorry, let me rephrase that. That's not inversion of control. That's a paradigm where the product controls the user, right? Inversion of control flips that around. I tell the coffee maker what to do. I put the pod I want in, and I'm not restricted by what the coffee maker wants, right? So the fancy word is I'm injecting what I want into the coffee maker, right? So now I have control, not the coffee maker, all right? And you'll see where this is used later on. But I wanted to just talk about that one broad concept in software engineering where inversion control means the higher level object, the higher level thing controls the bottom level thing, right? That's the flip of things, all right? So with that little tidbit out of the way, we'll start getting into the command template. We're going to start with subsystems. They're the most broad things that are out there, all right? So subsystems, remember, it talks to your hardware. So your hardware is going to be very different depending on the subsystem. Drivetrains have different hardware in them than shooters and intakes and so forth, right? So in the subsystem, when you create a subsystem in your code, there's really no requirements for what goes in there. You put what you want in there. All right. It has all the stuff that talks to the robot. All right. There's one important thing about a subsystem. Subsystems, remember, the commands control the subsystems, right? You push the button, the command fires, the subsystem goes. There are times when you don't want that to happen. So the default command says, if nobody's using me, I will go ahead and I will do this command. So it calls a command when it's free, right? But there's one important thing about the default command. It cannot interrupt any other command, okay? So that could pose a little bit of a problem, okay? And so I'm going to throw out a question for you guys, and if you want to throw a few answers into the QA, what you think it might be. So if a command runs a subsystem and it's doing a bunch of stuff, and the default command cannot override the command that was called, can anybody have any ideas on what might be a problem with that? I will give you a hint. The default command a lot of time is used for the drivetrain, right? So the joysticks, when nothing's going on, you're driving the drivetrain. Tell me any ideas where you think where the default command running and another command being triggered might be a problem in programming. So think about that, and I'll talk about it here in a second, all right? So all the methods that you want to expose, or all the functionality you want to expose, should, when you create them inside the subsystem, should have meaningful names, right? So if you have a intake for a subsystem, you don't want it to have, the intake dot do something, right? Or intake dot drive, which would make no sense, right? You want to have meaningful names. So some of the names might use like intake dot take in, or start, stop, intake dot eject. So you want to spit the ball back out, let's say, right? So you always want to make those names logical, because you might not be the one programming the command. And so the people that are using the subsystems should very easily understand what to call in the order they call it, all right? The other thing is in the command level, if you have a bunch of strange functions, if somebody else is trying to find a bug, they don't know what's going on, because these order of things don't make sense, because the subsystem doesn't have clear names. All right. Let's see. Anybody? I don't see any guesses at the default command. All right. So here, let me tell you about the default command and a problem that we experienced with in 2019. So as developers, your job is to help make driving the robot faster and easier for the drive team. So we had to pick up a hatch off of a wall, right? So if people were around 2019, it was basically a piece of polycarb that was about 2 feet in diameter with a small hole, and it was sitting in a pocket against the wall, and you had to pick it up out of the pocket. You couldn't just pull out. You had to pick it up before you could back away. So being smart programmers, we're like, hey, we could take care of that. You just push a button, we will lift it up, we'll back away a little bit and lower it and stow it, so that way it's all done faster than the human can do it. That was great. But the problem was, we could do that faster than the human player could do those operations and try to synchronize with the driver with picking it up, backing up, and lowering it. But it meant that once it was tall enough, or once it was high enough to clear, our driver wasn't waiting to do stuff. He was like, I want to start driving now. You could put it down while I'm driving, right? And so what happened was, they're trying to drive back, and our controls for the drivetrain to drive the robot were a default command. So he's trying to back up, but the command to raise, back up, and lower, which took like a second and a half, was still running. So he could not back up. So just be careful that when you're doing default commands, if somebody's using your subsystem, that you can't override them, and make sure that the functions that the drive team wants are proper. So just be aware of default commands. They can have those sort of like gotcha to it. All right. The next thing we're going to talk about are commands. Okay. So subsystems where you can do what you want, it's just hardware. Commands are different. Commands have the buttons that use commands are code that WPI wrote, right? So there's set methods that you have to have. There are 4 key methods that you need to have. If you don't, your code will not compile. First, I'll just go run through them. Initialize, execute, is finished, and end. If you happen to be a 2019 or newer person, you'll find out that interrupt is no longer here. That's gone. It's now just end. But anyway, so initialize. Initialize occurs as soon as you push the button or the command is then scheduled, it runs. And so you use stuff in there to sort of set the logic state inside the command to a known state, right? So common things you might do is if, let's say, you wanted to drive forward 5 feet when you push a button, the encoder value is what you're going to use to figure that out. But you need to know what your encoder value is now to figure out what the value should be at 5 feet. So maybe on the initialize, you push that, it reads the encoder value. So it sort of zeroes out your encoder value, right? Not zeroing out the encoder on the actual hardware, but just logically doing that. So that kind of stuff is done in initialize, right? Do not run any code in there, right? Just initialize values. Execute is where all your logic is. That's the beefiness of a command, right? There's one thing to point out. Execute is called every 20 milliseconds. It's a 50 hertz cycle time that the WPI framework is calling all your commands. You'll see why that's going to be important to know. So inside your execute, you can start reading sensors. You can tell, maybe you push a button and you tell the drivetrain to start driving forward at 50% power. Maybe you turn on an intake, or all these different things. Now, you can have one command control multiple subsystems. All right, you don't have to do one per. There's one thing to note about commands. When when you do inside your command, when you're coding, you will actually tell the framework which subsystems you need. It's called requires. So I say I require drivetrain, require this, right? So all those requires means I need a hardware resource, because subsystems are generally hardware. It will go through and tell all those subsystems, you stop doing what you're doing, because some command may be using you. I have a new command that wants you. All right? So execute is where things are running. Okay? So in the execute is where you do all your code and talking to the hardware and talking to the subsystem. Is finished is the WPI lib framework asking you, are you done running yet? Have you reached your goal? So if you're trying to drive forward 5 feet, the code inside is finished should be a simple check. My encoder value is 5. I need to be at 5,000. My current value is 4,000. I'm not done, right? It should be simple logic tests in there. Have I met whatever condition this command has, right? So every time a command is running, it's going to do execute is finished, and then moves on to the next command. Execute is finished, all right? It's always doing that loop, remember 20 milliseconds. If you say yes, I'm finished by returning true, immediately it will call end on your command, right? And so there, you're basically going to do anything you need to do to sort of like wind things down. So if you've reached your distance of 5 feet, you might want to stop. So end would say turn off the drivetrain, right? If you some things it may just be may not want to do it. Maybe end doesn't do anything, right? It depends on how you want the behavior to occur, because if you turn off and then the next command on the drivetrain turns it on, it may be jerky. So maybe you don't turn it off. So just think about what's going to happen after, and if nothing does happen, what do you want the state of all your different subsystems to be? Now, I talked about this loop, 20 milliseconds, 50 times a second. And by the way, that's configurable. You can make it faster if you want. And I'm not going to go into those details. That's more advanced stuff. But so let's sort of play through a scenario what's going on. So a driver pushes a button, and it's going to drive forward 5 feet, let's say. So they push the button. As soon as they push the button, initialize is fired, right? The initialize says, I know that this command needs the drivetrain. So it goes to the drivetrain and says, I have a command for you that's going to be starting. Stop whatever you're doing, right? Actually, let me phrase that. This command is scheduled. The framework knows about the other commands that are running and what they need. It finds out if any other command is using the subsystem that you want, in this case, the drivetrain. And then it tells the command you need to stop, which basically it calls the current running command, it calls the end on that function, on that command, right? And then shortly thereafter, when your command to drive forward 5 feet comes up and it's time to run, it will then call execute and is finished. So, right? And then it may call end if you return true. If you don't, it just calls execute and is finished. And WPI lib goes to the next command. It comes back to you again. And it calls execute is finished. Are you 5 feet? No. It goes around, comes back to you. Execute. Again, I'm still applying power to the drivetrain. Execute is finished. Oh, I've driven 5 feet? Yes. It then calls your end immediately and then at that point your command goes away, right? You're now finished, right? So I talked about, all these commands running. So that causes a problem. And there's something that you should be aware of that when you're doing this. So let's assume we have this, you're driving around, right? That's just a default command, let's say on the drivetrain. You have a turret and you want that always aiming at the target as you drive. And you're trying to run your intake. All right, so let's assume we're trying to gobble up balls while we're aiming at the target and driving around. So what's going to happen there is, let me make this a different color. Why? Oh, all right, so I'm yellow. Anyway, so that command's going to run, and it's going to do what it's going to do, right? And then 20 milliseconds later, it wants to run the aim command, and it's going to do what it does. And then it goes to the intake. And it's going through these things one at a time. Boom, boom, boom. Everything's happy. 20 milliseconds. That's really fast, by the way. 20 milliseconds. It's running all day long. So the problem you have is you have to be fast. You have to execute in a short period of time. What happens if inside a command, and let's say in our aiming command, it takes like 5 seconds. There's a bug in the code and it takes 5 seconds. I'm driving, I go here, I then get stuck for 5 seconds. Well, the drive command told the drivetrain a power, right? And so it's driving. The intake isn't doing anything. So the driver trying to, drive and turn. Unfortunately, because you stopped in this one command, it can't get around to the drive command to realize the driver is saying turn. So you have to be very, very careful that you do not take longer than 20 seconds. And it's really easy to make sure that doesn't happen. There's one way that if you're not careful, that you could cause something like this to happen, this long delay. And that is if you have loops. So if you have a while loop or for loop, and in your code you're iterating, you could actually cause it to block there. Now, another software engineering term is called a code smell. So a code smell is, imagine right now if you smell smoke, I'm guessing everybody's going to say, oh no, the house is on fire, let's get out, right? But if you're on your phone, because you're mobile now, right? You're watching this presentation on your phone in your car, sitting outside a barbecue restaurant, you're like, I can't wait for Mr. Carlson to get done so I can go ahead and eat some barbecue. So the idea that you smell something doesn't mean it's bad. It just means you should be aware of it. So I would say having a loop in your code doing the basic programming in the command template is a code smell. Make sure you look at it closely. Do you really need it? Because remember, this executes every 20 milliseconds. It's easy just to do one thing in here and let the main loop that's running can be the loop and not put the loop in your command. If it's valid to be there, that's fine. Just be very careful of that. All right. So I now have commands and I have subsystems. And in commands, there are 4 important things we need to have in commands, right? We need to have initialize, execute, is finished, end. Just memorize these 4. When you create a new command, it will automatically implement these things. So you don't have to know them and type them in yourself. your editor will put those in for you. But realize, initialize, set your variables you need to worry about, execute, do stuff. Is finished, read values, am I done? And maybe turn some stuff off if you want. All right, so that's what commands are. So there's something called a command group. And it turns out they're just a bunch of commands you put together. Because remember I said how I had that command that picked up that disk, backed away from the human player station and lowered it? We did that via command group. Now you could put all that logic into one command. But that one command then becomes, a single use thing. You can only use it for that, right? If I had to lift up, drive back, and lower as separate pieces, and I put them together in a group to be one virtual command, it allows me to say, you know what? I want the driver to be able to drive as soon as I get done raising it. So I go to the command group and I just remove the back away. So now it just says, actually just does lift up and, waits a second and lowers. Now use the drivetrain. So you could do stuff like that, and it's easy to change it around, right? Now, command groups, there are 4 types of command groups, and they have different ways of operating and different ways of ending. So the sequential command group is what we used for picking up that hatch, that disk, right? I needed to pick it up before I drove back, before I lowered it. Because if I picked it up and lowered it before I drove back, it wouldn't work. So I used, or our programmers used, sequential command group. It means do these commands in these orders, right? So A, B, and C. Just remember with default commands, you can't interrupt, right? So if you have any one of these commands and they don't end for some reason, if the first command to lift never ends, then your second and third command are not going to do anything. They're sitting and waiting for that first one to end. You have a parallel group. And the parallel group is different in that they run them all at the same time. So if I'm trying to drive forward and let's say I push a button, I want to drive forward and I want to place an object 5 feet off the ground, right? And so I push a button. I want to drive forward and raise my elevator at the same time. I could have my elevator lift while I say drive forward 5 feet, right? And when they're both done, right, because I need to be at my target and my elevator is at the right height, it will finish. So parallel commands, all commands in that group need to finish before that group is done. So that became a problem for us. So in 2018, we were doing some pathing, and we wanted to drop a cube into the target. It was called a switch. It was basically a big box in the ground for the people that don't know it. So you had to drop this milk crate in this box. And so we programmed the robot to go forward so many feet and then dump the cube. Well, because things aren't precise, if we say, and by the way, there's a really tricky rule here. If you were like an inch away from touching the box with your bumper in autonomous, actually no, if you're an inch away of touching the box and you put your cube in, it was a penalty. So you had to be touching the box. So what we did was, when we drove forward, we said, let's drive forward extra distance, right? So we know it's 4 feet. We're going to say 4 feet, 4.5, 4 feet and 1 inch, right? So that way we know we're touching. Since we're pushing up against it, it's clear to the judge, the referee that's refereeing that we're touching, right? But sometimes when you start our motors, if your wheels slip, you don't travel any distance, but your encoders increase. And so we drive forward and we don't touch. So we increase it to maybe like 2 inches, right? So now we're 4 feet, 2 inches. So we start up and we go and we hit the box. we've only gone 4 feet because we didn't slip. So the command's trying to go 4 feet too, but you've only gone 4 feet, and so it's still trying to drive forward, and you're never going to end because I want to shoot afterwards, right? So a lot of times we can use you can address that with doing a parallel in a race condition, right? So really what you want to do is you want to drive forward 4 feet, and you can put 4.5 feet, whatever you want. And if you know you're going to get there in a second and a half, you can start up 2 commands. One is basically drive forward, and I'm going to start a parallel race group. So I drive forward 4.5 feet in one command, and I have another command which is wait in a second and a half and end. So now I can drive forward, and one of those is going to finish first. And whatever one does, then that group ends. I can then go ahead and fire drop my cube, right? So, and there's some trickier ways you can do that in line, but that's one way of doing it. I want to show you the value of that group and why you'd want to use that differently. So finally, there's the third one, the fourth one, which is the parallel deadline group. So in the race group, what we found was I had a bunch of commands running at one time. Once any one of those ended, I wanted to stop everything, right? So let's go back to the elevator example, right? So I want to maybe raise the elevator. I may do 3 or 4 things while I'm driving forward, right? But when I get ready to put the element, that game piece on the target, I have to have gone 5 feet, right? And so I got a distance sensor, so I can measure how close I am to the target, or I'm not using encoders. So when I ask how far away from the target, and that's like less than 3 inches, go ahead and fire the piece. I want that command to be the command that says I'm done. So I could do all these things together, but that group is not going to finish until the distance sensor command reads you're close enough, right? So be aware of your ending configurations and what causes them to end, right? Sequential, one after another. If anything has a problem, the whole thing stops. Parallel, they all go separately, all in parallel, but the group does not finish until all of them are done. The race condition, they all go parallel. As soon as any of them stop, the whole thing stops. And then deadline is all of them in parallel. When this one stops, stop them all. And it allows you to orchestrate those commands in some pretty nice manner. Okay? So now we know about commands, we know about subsystems. We can sort of group some commands together, get some nice functionality. Yeah, we talked about buttons and stuff like that. So we haven't really talked about how do you sort of put it all together, right? We don't want to mess, and that's one of the things that's the beauty of the command template. We don't have this wiring mess, right? So the way we do that is inversion of control, right? So remember that Keurig, I put the coffee I want in there. So let's talk about that example. So it used to be people would program where they'd make a command, and inside the command, they created the subsystems they wanted in there. They knew what they needed. They just consumed them. So the command only did that. So an inversion of control changes that. So what you do is when you create a command, you pass in the subsystems you want to use, right? And you're like, well, why is that? I've moved it from this file to that file. It does the same thing. One of the cool things that you can do with inversion of control is, remember, all of our logic to the hardware is in the subsystem. So what if you made another object that didn't have hardware in it, but reacted like it did? Like if I tell it to, go a certain power, it said I'm going a certain power. And I put that into the command instead of the real hardware stuff. I don't need a robot, right? So that's injecting your dependencies. And I know teams like 1678 and some of the top teams do unit testing, and this is how they can test all their code later on. Now, again, that stuff is more advanced. A lot of teams don't do that. WPI Lab is going that way, but this is the reason why they changed it, was so that as you grow, and right now you get 50 lines of code and you can make it work, and you get that, in the next couple of years, you can learn more software engineering techniques where you could get to the point where you can start testing your code before you get a robot. All right. So that's the reason why I talked about the Keurig, because we're now putting in our subsystems into our commands. So when we start actually trying to wire these commands and subsystems together, there are basically 3 files you have to worry about, right? 2 of them, one of them you have to do anything with if you're just doing basic stuff, right? You could just, you'll just leave it alone, all right? So there's the constants.java, the robot container.java, and the robot.java. So let's go through this. Constants.java. So that one should only be constants that are static. Great things that could be in there is you could have maybe your diameter of your wheels. So that way, if you need to do the math to figure out the number of ticks per rotation to feet or some sort of distance, it's there. So all your constants are there. The other thing is they're public and static. That's fancy Java programming stuff. If you know it, great. You know what that means. If you don't, just make sure you always call them public and static. You can learn the Java as you go. You can copy paste. Just make sure they're public and static. All right. Not a lot to do in there. The bulk of your work is really in robot container. So if we go back to the Keurig example, right? I have my coffee cup pot. I have my coffee maker. I put what I want. I figure out what pot I want, and I put it in there. That's what this does. All right. We're actually going to make the coffee here. It's not going to run, but we're going to make the coffee here. And so since I need to put my subsystem in my command, you declare all your subsystems first, right? And you create them. And then you declare all your commands. And then you, as a parameter into the command, you pass in your subsystems, right? So that's the big thing you're doing there. Finally, the other thing you're doing is that first step in this process where the button fires off and actually calls a command. So in that, all those bindings where you could say, by the way, other things that you could put in into constants is you can put your CAN IDs and you can put your button numbers and stuff like that, so you can use names, right? You want your code to be readable. If you got, some value equals 5. Why is it 5, right? So you could declare a meaningful name in your constants, like wheel diameter in inches. And then, you could say, in your math, you can use wheel diameter in inches, and you know what you're doing. So it makes it easier to find bugs. All right. So, so in your bindings and robot container, you configure, basically tie the buttons or whatever triggers you have to your commands, right? The final one you use is robot.java. It comes pre-wired. If you create a new template and you say you're using the command template, it comes pre-wired. There's some stuff you can do that's more advanced. I'm not going to cover that here. In my final slide, there's a link to where the documents are and how you can go read about that. Don't touch that unless you know what's going on with that documentation. Leave this alone. This is the code that calls run on your commands. So if you happen to mess up the run command, that means that loop that says execute is finished, never happens. Kind of hard for your robot to move if the commands don't get called. So all that stuff is in here. It's more of a framework connectivity and operation thing than a logical thing that you're going to need to use. But once you get comfortable with everything else, go look at the advanced stuff and see some of the cool stuff you can add in there. All right. So that sort of wraps up the talk of how the command template works. Commands, subsystems, buttons, and groups. It's very easy to do it. When you create a, and by the way, if you have some questions, start filling them up here. I'll start paying attention for questions. So when you create a new template project in VS Code, it puts together all the stuff for you. It already has a sample command and a sample subsystem. Make sure you put them, when you make new ones, make a new one, put it there. You can look at the one that's there. It's very easy. All right. If you have any questions, you get any problems, you can always email me. Additionally, I do some programming classes, looking at doing later on this year, hopefully at the end of September, beginning of October, for beginning programming. It was like, I don't know Java, and I want to make the robot move. It's this kind of class. We go through a bunch of sensors and drivetrains and stuff. It'll be virtual, so you can program from home. We'll be using the new robot simulator in the 2020 framework to make that happen. Don't need a robot. You would need to have an Xbox controller for you to use. So with that being said, are there any questions about how the command template sort of operates and what your responsibilities are? Anybody by chance? Hopefully you're typing. All right, so inversion of control. So typically, if you think of another way of explaining it, so real quick, Samantha asked, can you explain inversion of control again? Samantha, real quick, that example didn't make sense, or you sort of missed a little bit? Okay. Okay, you missed part of it. Okay, so the Keurig is a coffee maker, right? And it takes these little pods. Let me go back to the slides so we can see what we're talking about. All right, so this coffee maker, the Keurig, takes these pods, all right? And I want to make coffee, and I want to choose what coffee I want to make. We agree I'm going to make coffee, right? So we have an agreed upon contract. I am not going to put like super glue in there, right? We agree I'm going to make coffee, but I want a different type of coffee than what they offer, all right? Unless Keurig sells me the pods with the type of coffee in there, I can't make it. So in this relationship, I don't get to pick what I want the coffee maker to do. The coffee maker is telling me what I can do, right? Inversion control flips that around. It puts the higher level entity in charge of the lower level entity. The higher level entity knows what it wants to do, and it's saying, I want you to do this, because you can do this, but I want you to do this on this thing, right? So I pass in the thing I want the Keurig to make. Here's my coffee, all right? And so that's the inversion of control. For years and years and years before this concept came up, it was the Keurig model. You could tell the Keurig what you wanted coffee, but the Keurig was in control of what coffee you made. All right. Does that make sense? If not, if you reply, that makes sense or not. That way I can make sure I got you covered. George asks, any books to study? Yes. So a couple things. If you're interested in software engineering, and these are, so George, I'm gonna answer this from a software engineering standpoint. If you want, like robotic stuff, that's the WPI libdocs. That's like, yeah, it works for robotics, but it's not general stuff. Two things I'd recommend on things of studying for software engineering. Okay, as a programmer, you do not want to be a Java programmer. You want to be a software engineer or programmer. The language is a tool to get things done. So if you understand broad concepts and how to do them, syntax is just something that gets in the way. You can figure it out. So in that, I would recommend two things. One is, and this one is really simple, and you can Google it, is something called the SOLID principles. SOLID, and it's a 5-letter acronym for 5 design patterns. If you do these 5 things, you get some really great software. And the second one to that one is design patterns. And design patterns came out in 1995. And it's the holy grail. That's the thing that started it all off. It turns out people started analyzing what everybody was doing, and they saw commonalities. And the idea behind design patterns is, if I tell you to do something and you then program it, you'll come up with a different way of doing it. And so they gave both senior level and junior level people and people in college different ways of solving problems. And it turns out people that were more experienced did it like 20 problems. They did it like 13 or 14 different ways. You can see they had a method of doing this one thing in multiple occurrences, where people that were less experienced, they did it, each way was unique to itself. So design patterns is a way of doing something that's been proven in how to do it, and B, it's a clear way of communicating how you want something done. And so the design pattern book called by the Gang of Four. If you Google Gang of Four design patterns, that'll be out there. They had about 20 or 30 design patterns. There's a bunch more now. And then later on, Solid took 5 of those key ones and came up with that. Solid principles, really important, really good. I actually have slide decks that I taught Solid principles at FRC, and I'll probably bring that back again. It's a great way of learning software engineering. Akash. As an example, would I collect my joystick inputs in the initialize method, actually run the arcade drive method and execute, and then call stop? No. So, no, don't do that, because if you want to read the joystick, as you know, it's going to read one time. It's going to read initialize reads once, and you're going to have that value the whole time, right? So you want to, every time you go through the loop, you want to read the joysticks, because they may be turning left or right, or they may be changing power at some point in time. So all that needs to be in the inside the execute. By the way, one comment I forgot to mention: when you schedule a command, execute will run. Sorry. When you schedule a command, initialize will run. Execute and is finished is not guaranteed to be called, because if before you get a chance to run, another command wants your subsystem, you'll never call your execute. But because somebody else took your subsystem before you got a chance to use it, it would call your end before it started running. All right. So, but if your execute is called, your is finish will be called. All right. Any other questions? So the question from Samantha, what's the difference between robot container and robot.java? So big picture, robot container is what you're concerned about. It's like, I want to wire this to this. I want to put these two things together, right? I want this command and this subsystem, right? Robot.java, think of that as that's the connection from your robot code to the FMS, all right? So that's all pre-wired and you don't need to mess with it, right? Robot.java is good unless you want to do some advanced stuff. But that's kind of like the FMS is calling those methods in robot.java, which is calling your commands to run. It does not run your commands in robot.java. It calls a command that calls the scheduler to run your commands, right? So FMS to code in robot.java, and then container is your commands to subsystems.
I really hate to interrupt this absolutely fascinating presentation. I'm not a programmer, and I found this enormously absorbing. But we've got about 2 minutes left. We got time for maybe one more quick question.
All right. So robotic students grades 6 or 8 seem to have problems visualizing the solution. How do we help them help? So I'm a very big proponent of project-based learning, and what I would do, and this is how I've done things. Sneak peek, if you want to get more about the details of how I do programming training, come to the how to learn more by listening less and doing more. What I do is basically project-based learning, and so what I'll do is I will give somebody who doesn't know how to program a working drivetrain with encoders, all that stuff already there, and the joysticks work, right? And I just ask them like, so these joysticks, and you push a button and it makes turns the motors on while they hold it, right? I give them that. And I'm like, so what I want you to do is I want you to push the B button to make it work. So all you have to do is copy a couple lines of code and tweak, right? If your methods are written very clearly, like button A dot while held, run command, turn on drivetrain, right? It's very simple for them to copy that, right? And so what I'm looking for is a bunch of small little things they can do. The next time I'm like, okay, can you make it turn it on in autonomous, right? So do simple things. Try to avoid using buzzwords, using concrete examples. Don't force them to learn concept and terminology at the same time. Email me after the fact if you want some more help. My information's there, and I can help you out there. By the way, before I started doing project-based programming, the first 3 years where I was working with programmers, I would start off with about 10 programmers. We lost about 70% of the programmers. By week 2 or 3, they would be then, there's nothing to do, I'm going to go do build. Since I did this project-based learning, I've retained 86% of my programmers. The whole season, they stay engaged.
Brian, I want to again thank you for a fascinating presentation. These are all being recorded. They will be posted on the Georgia First website, probably midweek to the latter part of the week. And if Brian's willing to make his slides available, those will be posted also. I want to thank everybody who joined us. As I say, I'm not a programmer. I found it just simply fascinating. Again, thank you all.
So it made sense to you?